I'm Daniel Spiewak. This is my talk on Shapeless, so if that's not the talk you were expecting, you're in the wrong room. And we're going to start off with a game. Look at these 4 slides and tell me which one was taken most recently. I can't really tell. Of course, the answer to this is Miles Sabin, who is best known for his work on the Scala Eclipse IDE. But in his spare time, he's been working on a project called Shapeless. And Shapeless is probably best known for things like HList and coproduct, which Martin kind of referenced yesterday with the whole scrap your boilerplate thing that Dottie is doing. But these tools are really just a demonstration of some tools and techniques for library authors to build better generic interfaces, right? And it's not tools and techniques as in thou shalt use HList and make your libraries awesome. It's tools and techniques like here's what you can do with the type system, and oh yeah, HList is one of the things that we can do with that. Shapeless is an exploration of some idioms for programming at the type level, idioms and patterns that allow us to leverage Scala's type system as a powerful programming language in and of itself. And most importantly of all, Shapeless is not magic. Miles does not have a special copy of Scala C that Martin Odersky gave him, blessed from on high, to do all of this stuff, right? We can do all of it ourselves in our own copy of Scala C for fun and profit. And so that's exactly what we're going to do. We're going to create our own Shapeless. And obviously we can't do all of it in this talk, but I think we can do some things, and I think we can learn a lot in the process. So a few years ago, I gave a talk entitled High Wizardry in the Land of Scala. And in this talk, one of the things that we did was we built an HList. A very, very, very straightforward HList. Basically, all it had was append, which was more or less the most complicated thing that you could do with HList back in Scala 2.7, which is when I gave this talk. But I think this is a pretty good building block. It's a pretty good place to start. We'll start with this HList kernel and build up some more functions on top of it that exemplify various techniques and idioms that we can use to do generic programming in Scala's type system. So here's HList. This is where we left off, I don't know, 8 years ago or whenever it was. We have an HList trait that has an append function, both at the value level and at the type level. These are both abstract, both the type and the value and the function. And we're going to have an hcons and an hnil implementation. I defined hnil as hnil not. There's a reason for this that I'll get to in a second, but basically it's to get around a bug in Scala's type system. You're going to find a lot of that sort of thing in these patterns for type level programming, is you just like, well, we just do it in exactly this way, because if we do it in this other way, that seems more natural. Scala C kind of explodes. So we don't want Scala C to explode. Anyway, hcons and hnil. So the append cases for hnil are very straightforward. They just return the list they're passed. And the append cases for hcons are basically what you would expect. We deconstruct the list, append to our tail, and then sort of put it back together again. And you notice that the append type level function is doing something a little bit weird, where it's doing this sort of projection on the t, where t is a variable that was given to the sort of type constructor hcons. This is one of the things that's gone in Dottie, so we wouldn't be able to do this in Dottie, but we're still in Scala land, so we're capable of doing this. And we'll come back to this technique in a second. We're going to need a package object that has some utilities in it to make things a little bit easier. We're going to have a cons type alias and a cons function. And the cons function, you'll see this a lot with type level programming, where instead of having member functions or methods, you have to actually put it on an implicit enrichment, which is what we're doing right here with this implicit syntax class. And the reason we're doing this is so that we can get the specific type of the list, which is the thing that we're dispatching on, type L. And you do this a lot because in type level programming, you spend all of this time trying to get a really, really precise type, only to have the compiler throw it away because subtyping. We don't want that to happen, so we use implicit conversions here to kind of get the cons function onto the list. So this is all just syntax, though, right? We're not doing anything useful, and we're not doing anything interesting. The interesting thing was kind of sort of a slide ago, and it's this append function, right? This is a type level function. It's the first of several type level functions that we will be seeing in this talk. And it's completely different than all of the others, because this is a context independent type level function. A very special sort of type level function. And again, it's one of those things that's going away, because in a sense, we don't really need it anymore once we get a little bit more power in the language. But as things currently stand, context-independent type-level functions are very special. They are structurally definitional. This is a property that they give us that is very, very powerful. This structurally definitional nature, and by the way, what I mean by that is like there's really only one way to define append, right? You could either define it like the H-nil way, or you could define it like the H-cons way, and there's kind of only one way to go, and it falls out very, very naturally from the structure of the data that we're working on. And this allows us to do some pretty powerful things. Like separation of concerns is something that we think about when we're doing programming just in general, right? This is an important sort of thing that we internalize when we're architecting software. And when you're doing software at the type level, it's also an important property. So separation of concerns in this context means we are allowed to define some sort of complex data, complex construct, a complex structure, and we can separate the nature of that structure from the nature of the operations we're performing over it by using a context-independent function to define the structure. This is really, really powerful. If we didn't have context-independent functions, anytime we defined a complex structure, we would have to redefine and reprove how to decompose that structure in every single operation. So that's really a pain, and context-independent functions allow us to get around that. They give us the same result regardless of scope. No one can import something and change what a type alias means. So that's a really nice property, and the compiler takes advantage of that. We can take advantage of that too. It is a type, right? So this append thing that we had on the previous screen, it's just a type alias. You can use it anywhere you can use a type. Whereas implicits, which are the other mechanism that you use for programming the type system, in fact, you use it most of the time, implicits are tied to function signatures, so you don't really have that option. And as I said, basically all of this stuff is gone in Dotty, right? We still have type aliases, but we don't have arbitrary sort of unbounded projection, because as Martin said, that's completely unsound. So we can't do this anymore. Well, we won't be able to do this anymore, but we can do it now, which is what matters. So make hay while the sun shines. There are some limitations here, and they're a doozy, right? Context-independent functions are limited in the way that they induct. You can only induct by open recursion, which is that sort of like unbounded type projection on the parameter thing that we did in HCons. That was super, super weird, right? That was like recursion in some sort of type alias. That's the only mechanism for induction that you have in a context-independent function. You don't get branching. There's no if then else. You can't say like, oh, if this type is a string, do this one thing, produce this one type, otherwise produce this other thing. That's not an option when you're just using type aliases. And you can't pair it with any complex value level transformations. The append function that we had on the previous, that we've been working with, that's paired with a value level transformation, i.e. appending two sort of lists of concells together, but the transformation is really trivial. It's so trivial that Scala C is able to track the equivalencies kind of at every step of the proof, and it doesn't lose track of its information. This is a very rare situation. Most of the time when you're programming at the type level and you're doing a type and value level transformation in synchrony, Scala C just loses its mind almost immediately. And you have to kind of prove things very, very carefully along the way and keep track of that information yourself. Scala C can't do it for you. So context-independent functions are very, very limited. They're very powerful. They give us this separation of concerns in this way. They're a nice abstraction here, but they're really not applicable to very many problems. Now, type constructors are context-independent functions. These are the type-level functions that I talked about in my talk, 8 years ago. Type classes are the way that we program the type system now. These are the cool new thing, but which has been around forever. And this is the only mechanism that we'll have for programming the type system in Dotty. And they are context-dependent functions. So context-independent functions are good, but they're very, very, very limited because they're basically giving us lambda calculus at the type level. And anyone who knows lambda calculus knows that it is Turing complete, but God, it's going to suck to prove that, right? Like, you can encode anything you want in lambda calculus, but you don't want to. Turing complete, not Turing pleasant. Context-dependent functions are really messy. Kind of the syntax is a little bit arcane. You're working kind of with this sideways abstraction thing, but they're way, way more powerful. And 99% of the stuff that we do with the type system, we're going to be doing with context-dependent functions, because rather than encoding lambda calculus at the type level, they give us Prolog at the type level. And everyone who knows Prolog knows that it's still not the most pleasant thing to work with, but it's dramatically more pleasant than the lambda calculus. So with a context-dependent function, we lose some flexibility. we're tied to function declarations. Dottie fixes this again, but right now we're tied to function declarations. Structural decomposition, that's what I was talking about before, where you're defining the shape of your data. That's tied to the operation you're performing with a context-dependent function, and you have to re-encode it in every operation. So you're basically stuck with really, really simple data structures. Not as much of a limitation as you would think, but still a limitation. But in accepting these limitations, we gain the ability to express arbitrary proofs at the type level. We express facts as implicit values, and then Scala C solves this proof for us by sort of traversing the exponential search space, which it takes about as much time as you would think. And one of the sort of random factoids of this is that problems like Towers of Hanoi or N Queens, which are like the hello world of Prolog, those are actually relatively easy to express in Scala's type system. So yeah, all of you who make money solving Towers of Hanoi just got a new tool. All right, with all of that out of the way, in this talk, we've already looked at append. We're going to look at 3 more type level functions. We're going to look at remove, map, and nth. These are functions that we're going to perform on HList. And nth you could also call this apply or index or something like that, or maybe get. Any of those would be valid. So we're going to look at the implementations of all 3 of these functions, starting with remove. Now, remove on HList is a type index deletion function. You take an HList, you take the remove function, you give it a type, and it will remove all instances of that type. So in this case, the result of the calling remove int is going to be false cons hnil. If we had more ints in here, like 2, 3, another 1, something like that, just sort of sprinkled around, the result would still be false cons hnil. Removes all instances of it. And if you don't have an int in your HList, it fails to compile. Clearly, this function is going to require a context dependence because we're doing type equivalency, right? We have to be able to check as to whether or not we're looking at the type that we asked to remove. We're also doing non-structural value manipulation. So an hcon cell is an hcon cell, regardless of whether or not it has an int or a boolean in it. There's nothing that structurally differentiates those two. So in order to be able to manipulate those 2 things differently, we need context-dependent functions. So how are we going to implement this? Well, what we're going to do is we're going to take the remove function and we're going to pull it out into an implicit syntax class, just like we did with the hcons, and then we'll define a type class that will have the implementation. This is a very, very, very common idiom. You take the method and you put it in the implicit syntax, and then all of the definition of the method is tied up in the implicit value that you get from the type system. And think of remover, which is going to have the implementation, not as a type class in like sort of monad or functor. Think of it like an implicit proof. The compiler is going to prove to us that it can remove a specific type from a specific list, and in the process of generating that proof, it will perform the removal. And now sometimes when you're programming at the type level, you don't actually have values because who cares about values? So if you're in that situation, you can actually just do the proof alone and you don't have to do the value level transformation, which is kind of fun. You end up throwing as instance of in there, and it's really random and feels kind of grody. HList syntax. This is sort of boilerplatey, right? This is the implicit enrichment that we had earlier. We're adding the remove function to it that takes some type parameter a and an implicit remover for a and the HList that we're targeting L. And right away, you'll notice something really bizarre here, which is that we have this r.out thing. This is a feature of Scala's type system called dependent method types. And what we're doing is we're getting the specific instance of the out type member from the R instance, right? So the instance of R that was generated by the type system, by this implicit, and passed into this function, that specific instance of R has an out on it. We're getting that out. And that's the type that we return. So the definition of remover, of course, has this out type that we talked about. And it has the apply that we were calling within the body. And this is basically the structure of it. We also, whenever we're using these out member types, these dependent output types, we generally have an aux type on the companion object. That's what you see at the bottom here. If you see this in Shapeless, this is what this means. This is one of those patterns that you can kind of have in your mind. Because it's really, really useful to be able to take this dependent output type and sort of lift it back into sort of a type parameter position. That's a little bit easier to work with, and it makes some of the definition sites a little bit less syntactically verbose. So, of course, the obvious question is, why are we using a dependent output type rather than just having a third type parameter on remover? Well, that's an excellent question. So, with type parameters, and type parameters specifically on the implicit sort of fact sites, the compiler has to solve all of the type parameters, right? It basically has to take every type parameter and put it into a fact set and then find a solution which manages all of those constraints. So in the case of remove, right, this is kind of a trivial example. So with remove, we're actually specifying, well, we want A to be an int, right? But in the general case, the compiler is going to have to solve this stuff. And so A becomes part of a fact set that the compiler is trying to solve. And it's going to solve it more or less from left to right. There are some exceptions to this, but it basically just drills through the parameter list and kind of goes in that direction. The problem is that partially due to bugs in Scala C, some types can't actually be solved like this. Some of this is kind of due to the infamous SI2712, which is of course fixed now. Some of it is due to various other de-aliasing things. But basically, as a general rule, Scala C can't do it all the time. Dependent type members are done a little bit differently. They don't go through the same de-aliasing steps, and so I think of them as being computed rather than solved. That's not a completely accurate metaphor, but it's close enough. And it's basically follows what we want to do here, right? So whenever we want to produce a result from an implicit computation, normally you want to stick that result in a dependent output type rather than an additional type parameter. This is, again, one of those patterns for programming the type system. Now, when you do this, you do accept a few limitations, and those limitations are precisely why the compiler is able to do what it does. The most notable of them is that you can't actually use it in a computational continuation. What I mean by that is you can't derive new implicits from this output type, right? So the out type on remover, like you can't take that and go find a new implicit that uses it as a parameter unless you use the aux type. Okay, so the aux type is basically why we have this, but again, the aux type then kind of goes back into, sort of de-aliasing weirdness land, so, you give up some of those benefits whenever you do it. Multiple implicit blocks, which Dottie is getting, do solve this problem. So Dottie is kind of the promised land, but we don't have them yet. And so because we don't have them yet, we have to accept these limitations. You can also do something Miles calls continuation passing at the type level. This is exactly as insane as it sounds. But if you're familiar with Scala Z's or Katz's unapplied type class, that's basically what it's doing. We're not going to go really into this, but just kind of know that if you hit this limitation, there are some support groups out there that you can talk to. Remover, okay, how are we going to implement this? Well, we're going to break it up into 3 different cases, and this basically mirrors how you would implement this function if you were implementing it at the value level. We're going to have a base case, which is the rightmost instance of the type to remove. So in other words, if you sort of deconstruct the list, it's the very, very last instance of that type. We're going to have an inductive rebuild case, which is not matching the type that we preserved. So in other words, we found a type to remove, we removed it, now we're putting the list back together again, and we're passing over types that we sort of don't care about, right? Types that we just want to put back in the list. And we're going to have an inductive remove case, which is where we're putting the list back together, and we're passing over types that we do care about, additional instances of the type to remove, so we pull them out of the list. And if you notice, there's actually an ambiguity here, right? Between the base case, which is, remove the rightmost thing, and the inductive case, the inductive remove, sort of remove the thing once we've already removed a thing. This is an ambiguity that we're going to have to teach the compiler how to solve. And to do that, we're going to use implicit prioritization. So when Scala C looks for implicits, one of the places it looks is the companion object of the type class that it's looking for. And specifically, it will look first at the companion object, then it will look at the supertype of the companion object, then the supertype of the supertype, and so on until it hits any. This is actually really, really powerful because it allows you to do, because you know that it's going to go in that order, you can put more specific implicit types, implicit facts in the subtype, i.e. in the companion object itself, and less specific, more general fallback cases in the supertype. And this allows you to kind of arrange things and deal with these ambiguities. So in this case, we're going to put the base case in a low priority implicits trait. And you notice this base case doesn't take any implicit parameters, which is your hint that there's no constraints here, right? It applies to any any type A, and any type A that's at the head of the HList, right? That's basically the only constraints that it has. So this is the more general fallback case. And the more specific case, the recursive remove case, it looks basically the same. We've got an A and an A that's at the head of the list, but we additionally take this implicit parameter that is, well, somewhere in that list we also removed another type. So this is the more specific case, we put it in the subtype. And you notice what we're doing here, this sort of definition here, right? This is that when you're reading these type signatures, when you're reading these implicits, your eye should always be drawn to the return type, because the return type is going to tell you how to interpret this fact, how to interpret the structure of this fact. So what we're saying here is we're declaring a remover for type A on some list that starts with type A and has a tail that's L. And then the return type, the return result, is the output of removing from the tail, which is what you would expect, right? If you're trying to remove some element and you find it in the list, you remove it from the list and then you remove it from the tail, and the return result is the remove from the tail. The third case that we have is the recursive rebuild, where we have two types A and B. A is the type that we're removing, B is the type that's at the head of the list. And when we do the removal, we just have to put B back onto that list, right? So this is, again, draw your eye to the output type. And for those of you who've been reading the value level, you notice that we actually did do that implementation there. But again, no one cares about the value level. It's not that we're paid to do that stuff or anything. So this is basically remover. This is all there is to it. And believe it or not, this is the most complicated type level function that we will be seeing today. Congratulations. Everything else we do today will actually be simpler, which is really, really cool and kind of indicative of what's going on. Because when you start doing this stuff, programming the type system, you actually realize that it's a lot easier than everybody kind of made it out to sound. You kind of do it, and then it works, and you're like, really? That's it? This is it. So we can move on to functions that sound cooler but are actually much, much simpler, like map. Now, map is an interesting function because whenever I talk to people, at conferences or meetups or things about Shapeless, invariably they will ask me, how does HList have map? Like, how is it even possible for that function to exist? And, it's a good question, and the confusion is really obvious, because if we look at functor, which is sort of the defining type class for the map operation, we take a type constructor f of a and add a function from a to b, and we return a type constructor f of b. Really, really straightforward stuff. But when you have an HList, there's an obvious problem. And that problem is, what is a, right? HList has many, many A's inside of it. Like, how do you answer this question? Like, what is A? What do you substitute in here? Is it going to be any? I hope not. Like, what do you do? So this is a really, really obvious conundrum. So we have to solve this problem if we want to implement map on HList. We have to find a way of encoding a function that can take many different sorts of A's and return potentially many different sorts of B's. And it has to choose which implementation it's going for based on the type that it's given. So if we can define this construct that is basically sort of fundamentally a set of functions indexed by type, and we choose the implementation of this function, the body of the function effectively, based on the type that we are applying to. And we make this choice at compile time. We don't want to be throwing match error, like, doing ugly runtime things, blah. Like, we don't want to do any of that stuff, right? We want to do this at compile time. And if we don't have a case for a particular type, we want to just have a compile error. We want that to blow up. So if we could build this construct, then in theory we could implement map, right? Because the hard thing about HList map is literally the function. So this would be the function. So how do we do this? How is this possible? Well, as with most things in programming the type system, the answer comes down to implicits. So remember I said earlier that implicit search considers the companions. And specifically, it considers the companions for all component types. So for example, if you're looking for a remover, it will consider the companion object for remover. And if you're looking for a list of remover, it will also consider the companion object for remover, which is really weird, but the collections library actually needs that functionality. Now, classes have companion objects, right? And objects are singleton instances of other classes, right? This is Scala 101. So this raises a really obvious question that is so obvious that I didn't think of it for like 10 years. What is the companion object for an object's class? The answer is the object itself. That's weird. Objects are like kind of this weird meta-circular thing. They are their own companion, which is really, really bizarre, and we could totally take advantage of that. So what we're going to do is we're going to have the object self-type, so the type of the class that is the object's sort of instance of, the object self-type will be a component of the type that we're trying to look up. And the object will contain an implicit case for each type that we're trying to index our polymorphic function on. And when we apply our polymorphic function, we'll look up that particular case based on the inferred type at the application site. It's easy to give a compiler when we don't find the type in question. It's simply implicit not found, right? And we can even annotate with add implicit not found and give our users a nice error message that says, don't apply the function to something that we don't have a case for. So we can kind of make this really nice to work with. It's very easy to have polymorphic functions that can be applied to many different types. All you say is like implicit def, foo for some type A, and then now you're polymorphic on all types A. Pretty great, right? And very, very, very good syntax and type inference. I can't stress enough how important this point is. If you come up with some crazy kitschy idea for like, here's some trick that I can do with the Scala language that programs the type system, but if users have to write down types that are like 6 pages long, no one will ever use it. Like, if it's really unpleasant, no one will touch it. So it's really important that you consider what is the syntax, what is the type inference. If you can't make both of those good, then you're just wasting your time. So this has really good syntax and really good type inference, and it looks like this. So here we're defining a polymorphic function called square that has 3 different cases, one for int, one for float, one for double, and it's just going to multiply the numbers by themselves and return the specific type. So if we apply it to an int, it returns an int. If we apply it to a double, it returns a double. If we apply it to a string, it does not compile because we didn't define a case for string, right? So this is basically the polymorphic function context. And I mean, this is not the most concise thing, but I think it's pretty good. And clearly, like at the call site, the syntax for it is excellent. So how do we define this? Well, we're going to start off with a poly trait. Poly is going to be a trait, and it's going to have an inner type called case, which has 2 type parameters, A and B. This is at the bottom here. And it has an apply method that takes an A and returns a B. This is literally function 1, but it's a different function 1. It's our function 1, and critically, it's an inner class of poly. That's actually very, very important. And we're going to have this at function, which is how we define cases, and it takes a type parameter A, and then returns a new type, which has an apply method that takes type parameter B. If you're not familiar with this new curly brace syntax, good, keep it that way. This syntax is very slide optimized. It turns into reflection at runtime, so you definitely don't want to do this in production. But I'm just doing it to kind of fit things on a slide. You don't have to use that syntax. Basically, it just means return a new anonymous inner class. And I'm doing this sort of hide the apply method inside of there, just so that I can make it so that users specify only type A. If I didn't do this, they would have to specify type A and type B, and I don't want them to have to do that. Remember, syntax is important. Supply type A, infer type B. And the apply method just takes the function, which is the body of this particular case, wraps it up inside of a case, and returns it. So when someone says at int and then lambda, sort of I, blah, 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 that is actually going to be of type case int to int. And then we define the implicit operator so that the type system can find it later, which we'll get to in a second. So then the question is, how do we define the application site, right? How do we apply this polymorphic function? This is how we define it. How do we apply it? Well, that's actually very straightforward. Poly is going to have an apply method that takes 2 type parameters, A and B, and it infers the A from the type of the thing that we're applying the function to. And then the B, it's going to go off into the implicit scope and find something of type this.case. This is really, really important. This.case. Now this is a component of the type. And in our previous example, this is going to be instantiated with square.type. And the companion of square.type is simply square. So the compiler will look in square to see if it can find a case for the type A that we applied to producing some type B. And if it finds it, it will allow us to apply it. So that allows this to work, which is really, really cool. We now have a polymorphic function. We can use this to do a lot of crazy things, like emulate JavaScript's, addition semantics, which is exactly what everyone wants. But aside from trolling your coworkers, this, this does have a few other downsides. Notably, you can't parameterize these functions, right? So remember in that previous slide where we were emulating JavaScript, that function was called add1. It wasn't called addn. We couldn't take a parameter. This is not as much of a limitation as you would think in practice, but it is slightly annoying now and again. So it's just something to think about. It's a limitation of the encoding. A more annoying limitation for me is that we don't have an anonymous syntax, right? Effectively, we have def, we do not have lambda, because there's no anonymous objects. So that's a little bit more annoying. It just means your code is more verbose. It's hard to pass these things around as a value because you have to kind of capture the precise type. And we've been doing that all along with our sort of HList syntax thing, the L extends HList. That's getting the precise type. But it's a little weird. So like, remember, syntax is important, inference is important. These are things that affect syntax and inference. So just like, keep in mind that there are some trade-offs for this. So if someone can find like some sort of magically clever polymorphic function encoding that solves these problems without sort of trading off other things, that would be really great. Go talk to Miles. As an exercise, if you're interested in those sorts of things, you can implement the sort of function composition on polymorphic functions, and also union, which sort of takes the set of cases from one side and the set of cases from the other side and returns a poly that has both sets of cases union together. These are very, very straightforward functions to implement, and they teach you a lot about type-level programming when you do them. So yeah, stuff to do at home later. So anyway, we've got poly, and I made the claim that we could use this to implement map. So let's see how that works. HList syntax is going to define our map method, and we'll have a p extends poly. And then we're going to look up some implicit proof called mapper that for this particular polymorphic function, we can map over the list. Basically the boilerplate that we had for remove, but with a different type level proof. Mapper's definition is almost exactly the same as remover. This is a really common theme, by the way. Almost all of your type level proofs are going to look like this in some way, shape, or form. So what about the definition? What are the cases? Well, like I said, it's simpler than remove. We have a base case, which is simply mapping over the empty list. And there's no restrictions on this, right? Regardless of what function you map over the empty list, it's just the empty list. So really, really easy to do. The recursive case is we have a polymorphic function. We have a list that starts with type A. We need to find a case, or specifically a p hash case. Remember, get the self type into the type component. A p hash case for type A that produces type B, and the resulting, now remember, have your eyes drawn to the sort of return type of the recursive case, mapper.aux. The return type is going to be b cons m.out. So map over the tail and take b, which is the result of the application, and put it back into the list. And this is actually all we need. Map now works. We can define an HList that has an int, a boolean, and a string, define a polymorphic function that transforms each of those cases, and lo and behold, we can map over it. That is really cool. And this is all we needed to do, right? See? No magic. No magic at all. A lot of strange tricks, but no magic. So what about nth? Now, nth is probably the weirdest function of all, because nth seems like it should be categorically impossible, right? Because what we're trying to do here is take an integer literal and use it to index into an HList, and get out the element that's at that particular part in the HList with the specific type that corresponds to that element. So if I say HList, nth 0, I want to get 42 of type int. If I say nth 1, I want to get false of type boolean. And if I say nth 2, I don't want it to compile. So how the heck can we make this work? How is that even possible? How do you index into an HList? Well, clearly, we're going to need some way of representing numbers at the type level. So I guess, sort of as a first start, we could define case object 1 and case object 2 and maybe case object 3, and this is a train wreck. Don't do this. It clearly does represent numbers. It will work. There's certainly nothing that says that, but you'd have to be typing literally for infinity to represent all of the numbers. So what would be a better thing to do is consider some prior art here, right? Let's go and see if there is a framework that maybe mathematicians or logicians have been using for years to structurally represent natural numbers, which is what we really need to index into things. And it turns out that there's a very well-known system called Peano Arithmetic, which has been around for 100 plus years. And Peano Arithmetic decomposes the natural numbers into two structural cases. One of them is conventionally called 0. In this case, I call it 0, 0, just to be really emphatic and also make the typer not hate me. And successor, right? So you have a 0, and then you have a successor which contains a natural number inside of it. So clearly, if you have this, then you can generate all of the natural numbers by just sort of having more and more and more and more and more and more successors, right? Relatively straightforward. Everybody should believe that. If once we have this representation, it should be clear that we can manipulate this and you sort of convert things back into ints if we wanted to, right? We could define this toInt function that takes an implicit proof toInt for some natural number n, and it's very easy to define this, right? The base case is simply 0. Right? And the successor case is, well, do the recursive sort of tail thing and then add 1 to that. No problem at all. And once we have this, we can take suck of 0, and it will tell us that that corresponds to integer 3. Right? So everybody should agree here that we have represented numbers at the type level. And these numbers do have some sort of value level representation, right? Suck is a case class, 0 is a case object, but this is not the most pleasant, value level representation at all, right? And if our users are having to write suck of suck of suck of suck of suck of suck of suck to get the sort of 40-second element out of our HList, they're just going to go away and leave us a bad review on Yelp. So what we really want to do here is we want to use int. Right? So can we convert from int into a natural number, or at least an int literal? Is that possible? Is there some way that we can make the compiler do this for us? And the answer is, yeah, there is a way. And that way is macros. Yay! No. Macros are terrible. Don't use them. But we're going to use them. They allow you to introduce new primitives into the language. And in fact, we're going to be using a special type of macros called white box macros, which allow you to introduce new primitives into the type system, which is categorically insane. They do not replace the existing type level facilities, right? So this is really important. If you come up with some crazy idea that's I want to represent, Bob's thingamajiggy at the type level, do not just write a macro, right? You write a macro to introduce a new primitive, and then you compose that primitive using implicits. Do as much as you possibly can with the functionality that's already in the type system. Macros are your last resort. Why? Because they're terrible, and they're probably going away. So don't use them until you absolutely have to. In our case, we absolutely have to. So here's what it looks like. We define this from int function on nat that takes an int and returns a nat, supposedly. And the definition of this from int is going to be defined by this materialize macro. This is valid Scala, by the way. So if it looks weird to your eyes, yeah, it should look weird. It's macros. And on the next page, we have a mountain of boilerplate, which is also macros. And basically what you should see here, sort of reading from the top, is we have a white box context, which should tell you, danger, danger, Will Robinson. And then on the next line, we import the entire freaking compiler. And I'm going to fade this out because we really shouldn't be looking at that. Here's the body of the macro. Here's the actual definition. Here's what we're doing. We're taking the integer as a tree, that's I, and we're pattern matching on it, and we're saying, oh, is it a literal constant integer whose value is greater than or equal to 0? If yes, then use quasi-quotes to create a 0, and then loop and sort of wrap around that 0 and just create more and more and more. Quasi-quotes are like, if you're familiar with sort of Lisp and how you use macros there and quotations, quasi-quotes are kind of like quotations in Scala. And we just build up this tree, and then we're going to return that tree, and the compiler will sort of realize that that is, in fact, meant to be a series of constructors, which is kind of cool. If we're not a literal constant integer whose value is greater than or equal to 0, we're just going to produce a compile error, which is what you want, right? If you're trying to create a natural number from -4, you want that to explode at compile time. And with this functionality, we can call the function and it works, which is cool. You call from int of 3, and you get suck of 0. So we can now convert in both directions, from integer literals to natural numbers, and from natural numbers back to integer literals. But that's still not quite enough machinery. Because remember, what we're doing here, like our motivating syntax does not include from int. I don't see any nat from int 0, nat from int 1, or any madness like that. All we're doing is using integer literals. So our conversion here is not explicit. If only there were some mechanism in Scala for taking conversions between two types that are explicit and making them, I don't know, not explicit, like some functionality that normally you wouldn't use, but this is evil day, so we're going to use it. Of course, implicit conversions are the answer to our problems. Said no one ever. We just add the implicit modifier, and magic happens, which is what everybody does when they add the implicit modifier. Hilariously and insanely, this works. I have no idea why this works. I'm pretty sure that at some point the compiler will just stop cooperating with me and it will no longer work. But for now, we can do magic. So implicit def from int, that's pretty cool. And that allows us to sort of, wherever we have an int, we can get a nat, just sort of magically from the compiler. So we've got our functionality now. We've got the ability to take integer literals and sort of push them up into the type level in a way that has really good syntax, because implicits. So how can we use that to implement nth? Well, we're going to go back to our HList syntax class, and we're going to add this nth thing, boilerplate just like we have, capture the precise type of the natural number, get an implicit proof called nther, right? All of us know how we're going to define nther. Like, we've seen it 100 times, or at least 3. So, you know, we're not going to do it again. And this should work, right? Almost. Almost. The problem is, because n is a polymorphic type here, right? So n is this type parameter constrained to be a subtype of nat. It turns out that the compiler will not trigger implicit conversions when you are in this situation, which is kind of weird, and I actually did not know that. But you know, if we do this, we can't use our magic thing that probably shouldn't ever work, but somehow works anyway. So we have to do something a little more clever. What we're going to do is we're going to go back to our nat trait, and we're going to put a type member on it, n subtype of nat. And this type member, n, is going to be the specific type of the nat itself, right? So for 0, this is, you know, type n is simply going to equal 0. For suck of, you know, n naught, type n is going to equal suck of n naught. It's going to be the self type of the nat. And what we can do now is we can go back to our dependent method types, and we can just take a nat, and then when we look for the nther proof, we look for the nther proof of lowercase n dot uppercase n. All of our variable names are confined to the same thing, apparently. N. This actually works. So the implicit conversion now triggers, because we're just looking for nat, and we have the specific self-type in our hand, so we can find the proof for the Peano numeral, and lo and behold, our syntax now functions as advertised. Yay! What? This is insane. All right, let's take a step back. Like, we're kind of way down in the weeds here. Let's take a step back and think about the horror that we just inflicted on the world, right? So 42 cons h nil, nth of 0. What is going on here? Well, there's an implicit conversion from int to nat that triggers a white box macro, that generates a Peano numeral, which is represented as nested type constructors. And then we use dependent method types to carry this type to the implicit block, and we find a proof that indexing is valid for this specific HList, and just for fun, we return the result. Abracadabra. So this begs an interesting question, right? We're doing things here that look very distinctly like Idris, very distinctly like Agda. We're taking these integer literals, these numbers, and we're moving them into the type system and working with them at the type level and then going back into the value level with those results. That's very much like a dependently typed language where, the value level and the type level kind of merge together in this sort of unholy synthesis of Mass Effect. Is that actually what we're doing here? Is Scala really somewhat like Idris, somewhat like Agda? Is that actually what it is? Yeah, I think it is. That's not scary or anything. The syntax is kind of bulky and awkward. Like we have to do this implicit stuff and all these white box macros and things. But yeah, actually this sort of works. That's cool. So yeah, tell your friends. So to wrap all of this up, we talked about context-dependent and context-independent functions and what you can do with them and why you would want to do one versus the other. We talked about forming implicit proofs, right? When you write a type-level function, you form an implicit proof of your action, encode rules as implicit values that the compiler will solve, and then use dependent output types to move the computed result from the implicit scope to the output type of your function. Speaking of the implicit scope, abuse the heck out of it. This is not your girlfriend. There are skeletons in the closet. Find them, tuck a note behind it. It's really, there's a lot of random stuff that you can do with the implicit scope that's really, really crazy. And you can get a lot done that way. And if all else fails, use a macro. Really, really, if all else fails. Really, 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 everything else failing, use a macro. But it's there for you if you need it. I don't know how much time we have, but are there any questions? Yes. I don't know if we have a microphone. I can just repeat the question.
Yeah, so what source of authority do you use when you create this wizardry? Do you look at the compiler sources, or how do you come up with
How do I come up with it? Well, that's better a question for Miles, because I come up with it by looking at his stuff. So Miles, do these things just come to you in visions, or how does it work? Miles, hang on a second. Microphone's coming.
So right at the beginning, basically, some kind of stochastic search process, I think, basically. If you imagine an infinite number of monkeys typing on keyboards, lots and lots of trying things which seemed like they might possibly work, realizing that they didn't, backing off and trying again, running into roadblocks. Like the one, for example, that Daniel was describing with the implicit conversions from integer literals to nats. I thought, oh my goodness, I've got this. It will work. I have this white box macro which will convert an integer literal to a nat.
It will work, in air quotes.
It does work. I can do it by hand, and it works. And then try it in the context of an implicit conversion. Suddenly, it doesn't work anymore. Oh no! All this work I've done in the last few days, none of it actually works. And then realize, okay, let's try again. There must be some other. So it's basically a very because really there is nothing. I mean, there's a lot of stuff here which is very principled, so it's using the type system. So a lot of the stuff that Daniel is describing in terms of thinking of implicits as proofs and making analogies with Agda and Idris, that's all true. However, mapping that onto the concrete reality that is the Scala compiler is not a logical or mathematical process. It's very empirical. It's very trial and error. And so basically, a ton of the process is mostly, I think, at the time when I was first doing this, it was just trial and error in terms of what's going to work, just treating the Scala compiler as a black box. Certainly since then, yes, a certain amount of looking at what's going on in the compiler internals, definitely.
I think that basically answers the question. All right, any further questions? We've got one back there by the camera. You should probably wait for the microphone as it sprints towards you.
If we lose arbitrary type projections and macros, how much of this remains possible?
Almost all of it. We lose type projections, but as I mentioned, Dottie is getting multiple implicit parameter blocks. And if you have multiple implicit parameter blocks, the advantages of type projections actually kind of go away. because this whole context dependence, context independence thing no longer matters if you have the ability to define your structural decomposition as one implicit and then carry it via a dependent type to the next parameter block and resolve more things on it. So it's basically the fact that we don't have type level continuations yet that forces us to use type projection. That's not an issue in Dotty. So that goes away. The lack of white box macros is a more serious problem. So that's going to be a problem for, obviously, int to nat, because we can't materialize that type without it. It's also a problem for Shapeless as generic. Miles has things that he wants to say. You can have, why don't you just come forward? We have a microphone.
So just on those two specific things, so there's one thing that Daniel said at the beginning, which was that Miles doesn't have his own version of the Scala compiler.
Okay, he does now.
So I do now. But it's not unique. It's not going to be unique to me for long. So I've been doing a certain amount of work as well as the SI2712 stuff. Some stuff I've been doing more recently is reviving the SIP 42.type, or otherwise known as SIP 23, which is the ability to basically treat literals as types directly in the surface syntax of Scala. So Adrian Moores did some work on that about a year and a half ago. It's been parked. I've recently picked it up. I'm aiming to get that in a usable Scala compiler, either the Lightbend Scala compiler or a type level Scala compiler, very, very shortly. So that addresses that particular one. In terms of multiple implicit parameter blocks, well, I do also have a patch against the Scala compiler which provides multiple implicit parameter blocks for Scala. It's actually many of these things are surprisingly small changes to the current Scala compiler. And I think there's actually a lot of opportunities for us to make this kind of idioms and the kind of idioms that you find in sort of type level Scala projects generally very much easier to use, I think. And I think certainly my plan is to over the next 6 months to a year is to basically see how much of this stuff can usefully and generally be rolled into the Scala programming language, as opposed to kind of waiting for something several years away.
All right, another question here. I don't know how long it will take that to sort of percolate to you through the layers of AstroTurf.
Thank you. I have a question about the context independence of the type level functions. I mean, yeah, it sounds relatively simple, but could you maybe, explain this once more in a more simple language? So what exactly this means?
So are you interested more in sort of why I called them that, or are you interested in why you would use one versus the other?
The first one.
Okay. I called it context independent versus context dependent because a context independent function is a type alias that cannot be changed by imports. It produces the same result regardless of the position you use it in the program. Whereas implicits are subject to implicit scope, right? So for all of this stuff that we're talking about, like defining the cases for mapper and whatnot, it's always possible for a user to just sort of define implicit mapper equals null and completely screw us up. So that makes it context dependent, right? You can do imports, you can do things like that. And this actually prevents the compiler, rightfully so, from proving certain things about these functions. So with a context independent function, the compiler can actually make those proofs, which allows you to do certain things that you can't do with implicits right now. The best example of what you can't do with implicits right now is basically what I've been talking about with structure, right? HList is a very simple structure. You have a con cell and sort of a nil, and it's very, very straightforward. But if you define something more intricate, that's sort of maybe some sort of graphish thing or like a tree that has sort of conditional branches, things like that, which I've done, if you do that at the type level, it becomes very painful to do everything with implicits because you have to redefine the way in which you decompose the structure in every single operation. So this is like take Wadler's expression problem and then choose the worst possible answer to it. That's what you end up with. Type projections give you a way around that right now. Multiple implicit parameter blocks give you a way around it for the future, because then you can define an implicit that proves how you decompose things and then carry that to your operation, which proves how you apply to that decomposition. I don't know if that makes sense, but I'm trying.
Something to think about, yes.
Okay.
Thank you.
I think the hook is coming from off stage, so thank you very much for your time.